Somewhere under the ice north of Alaska, a yellow cylinder about the size of a beer keg is climbing a wire. It hangs from a buoy frozen into the surface, and the wire drops beneath it into water more than 2 miles deep. The machine crawls up that wire at roughly 10 inches a second, which is slower than a person walking, and it does this a few times a day, every day, for as long as its batteries last. On the way, it swallows a thin stream of seawater through a little glass tube and measures how well that water conducts electricity. That single reading, converted, tells you how much salt is dissolved in it. Depth, temperature, salt. Over and over, from about 2,500 feet below the ice, all the way up to the underside of the floe. When it reaches the top, it sits there for a while, and a small antenna sticking out of the ice pushes the day's numbers up to a satellite. Then the cylinder lets go and sinks back down, and the whole thing starts again. The instrument is called an ice-tethered profiler. Woods Hole. Oceanographic Institution has been putting them out on Arctic ice since the mid-2000s, and the reason they exist is that the Western Arctic Ocean does something no other ocean on this planet does, and nobody could watch it happen year-round until these things were invented. Ships can only get up there in late summer. The ice closes behind them. For 8 or 9 months a year, the region simply went dark, and everything anyone knew about it came from a handful of expeditions, some Cold War submarine transects, and a lot of educated guessing. So here's what the wire sees. Right at the top, just under the ice, the water is close to fresh. Not fresh the way a river is fresh, but far less salty than any ocean water has a right to be. Go down 100 feet, and it's saltier. 200 feet, saltier still. Somewhere around 600 feet, the salinity climbs through the value that oceanographers treat as the Arctic's own average, and then it keeps rising toward numbers you'd recognize from the open Atlantic. Down at 1,000 feet, the water is not only salty, it's warm. Warm in the polar sense, which means a few degrees above the freezing point of seawater, maybe 34 or 35 degrees Fahrenheit. That doesn't sound like much. It's enough heat, if it ever got to the surface in bulk, to melt the ice cap above it several times over and keep going. It doesn't get to the surface. That's the first thing worth understanding here, and everything else in this story hangs off it. Between the ice and that warm, salty layer sits a lid. Not a physical lid, a density lid, built entirely out of the fact that the top of this ocean is fresher than the bottom. Fresh water is lighter. Light water sits on heavy water. And in the Arctic, the difference in saltiness is so large that no realistic amount of cooling, wind, or storm activity can mix through it. The layers are effectively welded in place by their own weight. That lid has a name. Oceanographers call it the halocline, from the Greek for salt, and it is the single reason there is a permanent ice cover on the Arctic Ocean at all. Take away the fresh top layer and you'd have warm Atlantic water reaching the surface in winter, and the Arctic would look like a very cold version of the northern Norwegian coast, which stays open water all year round for exactly that reason. The Barents Sea, right next door, mostly doesn't freeze. Same latitude, different stratification, meaning the fresh water on top of the Arctic isn't an accident of the system. It is the system, and in the western half of the basin, in the deep bowl between Alaska, the Canadian Arctic Islands, and the North Pole, that fresh layer gets thick, very thick, thick enough that if you could somehow strain out every molecule of pure fresh water mixed into the column at the center and stack it up on its own, you'd have a layer of drinkable water roughly 80 feet deep sitting over water 2.5 miles deep. Spread that across the whole region, and you get a volume that is hard to hold in your head, roughly 23,000 cubic kilometers, somewhere around 5,500 cubic miles. For an American audience, there's a comparison that lands almost exactly. All 5 Great Lakes, Superior, Michigan, Huron, Erie, and Ontario, added together, every drop, come to a bit under 23,000 cubic kilometers, which puts the fresh water piled up in the western Arctic Ocean to within the error bars, at the entire Great Lakes system, sitting in the ocean. Not in a basin with shores and a shoreline and a bedrock floor, but suspended in salt water, held there by nothing you can touch, held there by wind. That's the part that takes some getting used to. There is no dam. There's no sill, no ridge, no narrowing, no geological feature doing the work. The reason that water stays in a heap in the Canada Basin, instead of spreading out across the Arctic and draining south into the Atlantic, is that the atmosphere above it turns clockwise, more or less permanently, and a turning atmosphere over an ocean pushes surface water toward the middle of the turn. Pile enough water into the middle, and it forms a shallow dome, a hill of sea surface a few inches high and several hundred miles across. And once you have a hill, you have a slope. And once you have a slope on a rotating planet, you have a current running around it. The current holds the pile. The pile drives the current. The whole thing turns slowly clockwise, in a bowl of its own making, under a lid of ice. It's called the Beaufort Gyre. It's the largest reservoir of fresh water in the Arctic Ocean, and one of the largest anywhere on Earth that isn't a lake or an ice sheet. And its entire structural support is a pressure pattern in the air. Now, between the early 2000s and the middle of the last decade, that reservoir got noticeably bigger. Not slightly, measurably, repeatedly, in survey after survey, by a margin far outside what the instruments could plausibly be getting wrong. Ships went back to the same stations every summer and found the fresh layer deeper than the year before. The satellites watching the height of the sea surface saw the dome rising. The moorings sitting on the seafloor, listening upward, saw the ice change, and the water column change with it. The gyre took on something like 6,400 cubic kilometers of extra fresh water in 16 years. That's about a Lake Michigan and a third, added to a system that already had a Great Lakes worth in it, in less time than a mortgage. And this is where the story stops being a nice piece of physical oceanography and starts being an argument, because a reservoir held in place by wind is a reservoir that can be let go by wind. The pattern that spins the Beaufort Gyre clockwise has, in the historical record, reversed. It's done it before, more than once, and when it does, the pile relaxes. The fresh water spills out of the western Arctic and works its way toward the North Atlantic. That's not a hypothesis about the future. It happened in the 1980s and 90s, and there's a well-documented earlier event running through the 60s and 70s, where a slug of Arctic fresh water went around the entire North Atlantic subpolar gyre and changed the salinity of the water column down to half a mile deep for more than a decade. The North Atlantic, as it happens, is where a large part of the global ocean's deep circulation gets started, and it gets started by surface water becoming dense enough to sink. Salt is what makes it dense. Fresh water is what stops it. So the question sitting underneath all of this is straightforward to ask and very hard to answer. There is a Great Lake-sized volume of fresh water perched in the Arctic, kept there by an atmospheric pattern that has historically flipped every decade or so. What happens when it lets go? How fast can it actually come out? And does the North Atlantic care? Those three questions have three different quality levels of answer. And one of the things worth doing here is keeping them apart, because they routinely get blended into a single dramatic statement that the evidence does not support. The volume is measured. The release mechanism is partly measured and partly modeled. The consequence downstream is, right now, an open scientific argument in which the observations and the models disagree with each other in ways nobody has fully resolved. But before any of that, the machine itself. How the water gets in, why it floats, why it stays, and what it's doing for the planet while it sits there. Start with the water. There's a problem with saying an ocean contains a certain amount of fresh water, and it's worth dealing with immediately. Because the entire quantitative side of this subject rests on how it gets solved. You can't go out to the Beaufort Sea and scoop up fresh water. There isn't any. Every drop up there is salty to some degree. What there is water that is less salty than it would be if the fresh inputs had never arrived. So the number you keep hearing, 23,000 cubic kilometers, describes a deficit. There's no substance sitting up there to weigh. Here's how it's actually done. You pick a reference salinity, a number that represents what the water would be without the extra fresh input. For the Arctic, the convention since the 1980s has been 34.8 parts per thousand, which is roughly the average salinity of the whole Arctic Ocean, including its deep water. Then, at every depth in your profile, you ask a simple question. How much pure water would I have to remove from this parcel to bring it up to 34.8? Add those answers up through the column and you get a thickness. So many feet of fresh water equivalent contained in that column. Do it at every station across a region, multiply by area, and you get a volume. So much for the arithmetic. It sounds bloodless, and it matters enormously, because it means the headline number is only as meaningful as three private choices: which reference salinity you used, where you drew the edges of your region, and how deep you integrated. Change any of those, and the number moves. Some published estimates put around 45,000 cubic kilometers in the Canada Basin, roughly double the figure I've been quoting. And the difference isn't a disagreement about the ocean. It's a difference in where the box was drawn and how deep the counting went. The commonly quoted figure for the Beaufort Gyre comes from a specific box: 70 to 81 degrees north, 130 to 170 degrees west, restricted to water deeper than about 1,000 feet, so the shallow shelves don't contaminate the accounting. That box has been surveyed the same way, with the same conventions, every year since 2003, which is why its numbers are worth something. Consistency over time is worth more here than any single beautifully precise measurement, and the people who set that program up understood that from the start. The reservoir, then, is a deficit of salt, measured against a convention, inside a box somebody chose. Every honest sentence about it carries those three qualifications, and I'd rather put them at the front than pretend the number arrived from nowhere. Now, where does the deficit come from? 4 sources, and they're wildly different in character. The first one is rivers, and the Arctic's relationship with rivers is a peculiar one. Look at a globe from the top, and you'll notice something that a normal map projection completely hides. The Arctic Ocean is almost surrounded by land. It's a nearly enclosed basin, about 5.5 million square miles of it, with one wide doorway to the Atlantic between Greenland and Norway, one narrow doorway to the Pacific, and a maze of Canadian islands in between. And the continents that ring it, Siberia and northern North America, drain enormous territories northward: the Yenisei, the Lena, the Ob, the Mackenzie. Names most Americans have never had a reason to learn, and every one of them is a monster. The Lena alone carries something on the order of 580 cubic kilometers of fresh water a year out of central Siberia and into the Laptov Sea. The Mackenzie, draining a fifth of Canada, delivers roughly 300 cubic kilometers a year into the Beaufort Sea, most of it in a violent burst during the spring breakup, when the ice on the river gives way, and half a winter's worth of accumulated snowmelt comes down the channel at once. Add up everything that flows into the Arctic, gauged and ungauged, and you land somewhere near 4,200 cubic kilometers a year, with an uncertainty around 10% because a lot of the smaller Siberian and Canadian catchments have never had reliable gauges on them. Now put that next to the size of the ocean receiving it. The Arctic is about 1% of the world ocean by volume. It receives roughly 11% of the world's river discharge. That ratio is the whole reason this ocean behaves the way it does. Take the Atlantic or the Pacific and pour a continent's worth of rivers into it, and the rivers vanish. Their fresh water is a rounding error against the volume of salt water available to dilute it. Do the same thing in the Arctic, and it doesn't vanish at all. It sits there. It spreads out across the top because it's lighter, and it stays on top because there's nothing energetic enough at those latitudes to force it down. Watching it happen from orbit in June is one of the more striking things in Earth observation. The Ob and Yenisei plumes come out into the Kara Sea, and you can see them. A visibly different color, spreading north and east across an area the size of a Great Plains state. The Mackenzie's plume comes out brown with silt and pushes into the Beaufort Sea, and depending on which way the wind is blowing that summer, it either hugs the coast and heads east toward the Canadian islands, or it gets shoved west and offshore, out into the deep basin where the gyre can get hold of it. That fork in the road, incidentally, turns out to matter a great deal, and we'll come back to it. The rivers also have a rhythm that the ocean doesn't. 90% of a Siberian river's annual discharge can come through in a few months. In the deep winter, the same channel is nearly dead, locked under a couple of feet of ice, discharging a trickle. So the Arctic doesn't get a steady drip of fresh water. It gets an annual pulse, a slug of it every early summer, arriving at the same time as the sea ice starts melting and the surface layer is already at its freshest and most fragile. And that discharge has been increasing. The gauged records from the big Eurasian rivers, some of which run back to the 1930s, show a rising trend, and the Arctic Report Card has flagged record, or near record, combined discharge years repeatedly over the past decade. The increase is not enormous in percentage terms. It's a few percent per decade. But it's persistent. It's showing up in independent measurements, including the oxygen isotope composition of the water itself. And it runs in the same direction as everything else happening to this ocean's freshwater budget. Warmer atmosphere holds more water vapor. More of it precipitates at high latitudes. More of it ends up in the rivers. More of it ends up here. Rivers, then, are the biggest single source. Roughly 40% of the fresh water arriving in the Arctic each year comes down a river channel. But they're not the source that ends up in the Beaufort Gyre in the largest quantity. That distinction belongs to something else entirely, and it comes in through a gap so shallow and so narrow that you could almost mistake it for a mistake in the plumbing. The Bering Strait is 53 miles wide and about 165 feet deep. That's it. Between Cape Dezhnev in Russia and Cape Prince of Wales in Alaska, with two small islands sitting in the middle of it, there is a gap you could swim across in a very bad afternoon. Floored at a depth a modern container ship's hull would nearly scrape if the ship were unlucky. Through that gap, water flows north, continuously on average, year after year. It flows north because sea level on the Pacific side sits a little higher than on the Arctic side, a difference of about 1.5 feet maintained by the large-scale density structure of the two oceans. It's a permanent tilt, and water runs downhill even when the hill is made of nothing but a difference in how salty two oceans are on opposite sides of a continent. The volume moving through is around 1 million cubic meters per second in the annual mean, which oceanographers write as 1 sverdrup. For scale, that is roughly 50 times the flow of the Mississippi River at its mouth, pushing through a gap narrower than the distance from Manhattan to Bridgeport. And crucially, that Pacific water is fresher than Arctic water. It runs around 32 parts per thousand, against the Arctic reference of 34.8. So every cubic meter that comes through the strait carries a freshwater surplus with it. Do that accounting over a year, and the Bering Strait alone delivers something in the range of 2,500 cubic kilometers of fresh water into the Arctic, which is a bit more than half of what all the rivers combined manage. Rebecca Woodgate and her colleagues at the University of Washington have kept moorings in that strait almost continuously since 1990, which is one of the longest single-point ocean records anywhere in the polar regions. Their data show the through-flow strengthening, something like a 50% increase in volume transport between the early 2000s and the early 2010s, from around 0.7 sverdrups to around 1.1. More water, and the water is warmer, and the water is fresher. All three trends push the same direction. Now that Pacific water doesn't stay at the surface. It's fresher than deep Arctic water, but it's saltier than the very top layer, so once it gets into the basin, it slides in underneath the surface layer and above the Atlantic water, and it forms its own distinct slab in the water column. Two slabs, actually, one from summer inflow and one from winter inflow, sitting at slightly different depths with slightly different properties. Anyone reading a salinity profile from the Canada Basin can pick them out immediately, the way you'd pick out a stripe of a different rock in a cliff face. The Canada Basin has a particular quirk in this respect. Work by Michio Yamamoto Kawai and colleagues, using the chemistry of the water itself to fingerprint where each molecule came from, found that Pacific inflow accounts for as much as 3/4 of the total freshwater input to that basin. River and precipitation water together, what oceanographers lump under the term meteoric water, add several hundred cubic kilometers a year on top of that, which makes the Beaufort Gyre, in a real sense, more Pacific than Siberian. The bulk of what's piled up there came through a shallow slot between Alaska and Russia, not down a river. Most people guess rivers, and it's easy to see why. Rivers are visible and dramatic, and they photograph well. The Bering Strait through flow is invisible. You could sail across it and see nothing at all. The third source is the sky. Over the Arctic Ocean, more water falls as precipitation than evaporates back off, and that surplus, in the range of 2,000 to 3,000 cubic kilometers a year, depending on whose reanalysis you use, is a genuine freshwater input. The uncertainty on that number is uncomfortably large because measuring snowfall over sea ice is close to a nightmare. Gauges under drifting Arctic conditions catch a fraction of what actually lands. Blowing snow gets counted twice, or not at all, and satellite retrievals struggle to distinguish a snow surface from a snow cloud. So this term is the softest one in the whole budget, and anyone quoting it precisely is overselling. The fourth source is the ice itself, and it works in both directions. When seawater freezes, the ice crystal structure rejects most of the salt. Not all of it. Some gets trapped in tiny brine pockets between the crystals, and those pockets slowly drain downward over the following months, so first-year ice is much saltier than multi-year ice. Old Arctic ice can be fresh enough to melt down and drink. Explorers did exactly that for a couple of centuries, and the older and more weathered the flow, the better the water. What that means physically is that freezing separates the water column. It pulls fresh water out of the top and stacks it up as ice, and it dumps the rejected salt back into the water underneath as dense cold brine, which sinks. Melting does the reverse. It puts fresh water back into the surface layer, right where it does the most to strengthen the density lid. So over a year, the ice acts like a battery. Fresh water gets locked up in autumn and winter and released in spring and summer. In a stable climate that battery cycles, and the annual net is close to zero. The Arctic has not had a stable climate for the last 40 years. Since satellite records began in 1979, the September sea ice minimum has declined by something in the neighborhood of 12 to 13% per decade, and the ice that remains is thinner and much younger. The thick multi-year ice that used to dominate the Central Basin, ice that had survived 5 or 6 summers, has largely gone. What's left is mostly ice that formed the previous winter, and when ice that had been in storage for years melts, that's not a cycle, that's a withdrawal. The fresh water locked up in that old ice goes into the ocean and stays there. Estimates for the Beaufort Gyre region attribute roughly 500 cubic kilometers of the freshwater increase to net ice melt, which is around 8% of the total gain. Not the dominant term, but not nothing, and it arrives in exactly the place where it has the most leverage. Put all four together, and you have an ocean receiving roughly 9 or 10,000 cubic kilometers of fresh water every year from rivers, the Pacific, the sky, and the ice, delivered into a basin that is small, shallow around its edges, and almost entirely enclosed, which raises the obvious question. If it's been getting that input for thousands of years, why isn't the Arctic Ocean simply fresh by now? Because it leaks, steadily and in the long run, at very nearly the same rate it fills. There are two ways out of the Arctic Ocean, and both of them lead to the same place. The first is the wide gap between Greenland and Svalbard, a stretch of deep water where the Arctic empties southward along the Greenland coast. Liquid fresh water leaves through there at something like 2,700 cubic kilometers a year. With an uncertainty of a few hundred either side, and a comparable volume leaves as ice, carried south in a conveyor of flows that keeps going until it hits water warm enough to finish it off. That ice export has been falling by something on the order of a quarter per decade across the 1990s and 2000s, which is its own subject and a large one. The second exit is the Canadian Arctic archipelago, that shattered maze of islands and channels north of Hudson Bay, where water threads its way south through a set of narrow passages and comes out into Baffin Bay, then through Davis Strait, then into the Labrador Sea. This route carries more liquid fresh water than the Greenland side does, roughly 3,200 cubic kilometers a year at Davis Strait, according to multi-year mooring records, plus another 800 or so as ice. That second route is the one that ends up mattering most for reasons that only become clear much later. Add the exits up, compare them to the inputs, and the books roughly balance. Roughly. Every one of those flux numbers has an uncertainty of 10 to 20%. And when you're subtracting two large numbers of similar size to get a small residual, that uncertainty eats the residual alive. This is a chronic problem in the field, and there's no clever way around it. You cannot determine how much fresh water the Arctic is gaining or losing by measuring what goes in and what comes out. The error bars are wider than the signal, which is precisely why the survey program matters. If you can't get the answer from the fluxes, you get it from the storage. Go measure the reservoir directly year after year with the same method, and let the change in the reservoir tell you what the fluxes must have done. That's the logic that put ships and moorings and profilers into the Beaufort Gyre in the first place, and it works. Now, the physics of why any of this holds together. In most of the world's oceans, temperature runs the show. Warm water is light, cold water is heavy, and the density structure of the tropical and temperate ocean is basically a thermal structure. Salinity matters, but it's the junior partner. At high latitudes, the ranking flips, and it flips for a reason that comes down to the shape of a curve. Seawater's density doesn't respond to temperature in a straight line. It responds much more strongly to a 1-degree change when the water is warm than when the water is cold. Take water at 80 degrees Fahrenheit and cool it by 1 degree and you get a real density increase. Take water at 30 degrees Fahrenheit and cool it by 1 degree, and the density barely moves. The curve flattens out down there. Salinity's effect on density does not flatten out. It's essentially linear across the whole range. A given change in salt content gives you a given change in density, whether the water is tropical or freezing. So in the Arctic, where the entire upper water column sits within a few degrees of freezing anyway, temperature has almost no leverage left, and salinity is doing effectively all the work. That single asymmetry sets the structure of the entire basin. The Arctic is a salinity-stratified ocean, and it behaves in ways that would be impossible in a temperature-stratified one. The most important of those ways is this. In the Atlantic, when winter comes and the surface cools, the surface water gets denser and sinks, and the column overturns, and heat from below gets mixed up and lost to the atmosphere. That's convection, and it happens every winter across large areas of the subpolar North Atlantic. It's how the deep ocean gets ventilated. In the Arctic, winter cooling can't do that. The surface water is already at the freezing point. You can cool it forever, and it will not become dense enough to sink through a layer that's several parts per thousand saltier underneath, so the column doesn't overturn. The surface layer just freezes instead. That leaves the warm Atlantic water sitting down there at 600 to 2,000 feet, isolated. It comes in from the Nordic seas, having lost its buoyancy up there, and it slides in at intermediate depth and circulates around the Arctic basins counterclockwise, following the continental slopes over a period of years to decades. It carries a serious amount of heat. Estimates of how much ice that heat could melt, if it ever reached the surface, run into the multiple meters of thickness per year across the whole basin, which would eliminate the Arctic ice cover in a couple of seasons. It doesn't reach the surface because the halocline is in the way, and the halocline is made of the fresh water we've been talking about. Let me put that plainly because it's the load-bearing sentence of this entire subject. The Arctic Ocean has ice on it because it has fresh water in it. The fresh water is what keeps the heat down. There's a natural experiment sitting right next door that proves the point. The Barents Sea, north of Norway and northwestern Russia, is at the same latitudes as much of the Arctic basin. Parts of it sit above 80 degrees north, and large stretches of it don't freeze in any month in most years. Warm Atlantic water enters it directly at the surface, and there's no strong halocline to stop that water from mixing and giving up its heat to the air. Ships have used Murmansk as an ice-free port since the First World War. It's the northernmost ice-free port in the world, and the reason isn't latitude or luck, it's stratification. Two adjacent stretches of ocean at the same latitude, one covered in permanent ice, and one open year-round, and the difference is a few parts per thousand of salt in the upper few hundred feet. That should tell you how finely balanced this arrangement is. What's holding it up is a stack of layers sorted by density in a particular order, maintained by a supply of fresh water on top and a shortage of energy available to mix it down. The margins involved are narrow, so the next question almost asks itself, what happens when you take that fresh water and concentrate it in one place instead of spreading it evenly? In the autumn of 1893, a Norwegian ship called the Fram let itself get frozen into the ice north of Siberia on purpose. Fridtjof Nansen had built her with a rounded hull specifically so that when the pack squeezed, she'd pop upward instead of being crushed, and his plan was to let the ice carry the ship across the top of the world. It worked, more or less. The Fram drifted for 3 years and came out near Svalbard, and Nansen came home a national hero. Along the way, he kept meticulous records of where the ship went and which way the wind was blowing, and he noticed something that bothered him. The ice did not drift downwind. It drifted consistently off to the right of the wind, by somewhere between 20 and 40 degrees, every time. He couldn't explain it, so he did what a good scientist does with an anomaly he can't crack. He handed it to somebody else. The somebody else was a graduate student named Vagn Walfrid Ekman, working under Wilhelm Bjerknes in Sweden, and in 1905 he published the explanation. The wind drags the very top layer of the water. That layer, once moving, is deflected by the rotation of the earth. It drags the layer beneath it, which is deflected a bit further, and so on downward, each layer weaker and rotated further, until the motion peters out a few hundred feet down. Draw the velocity vectors of all those layers, and they trace a spiral. Ekman's spiral. It's in every introductory oceanography course on the planet, and it came out of a Norwegian explorer being annoyed by his own navigation data. The consequence that matters here is what happens when you add up the whole spiral. Integrate the transport through the entire wind-driven layer, and the net movement of water is 90 degrees to the right of the wind in the northern hemisphere, not 30 degrees, a full right angle. The wind blows one way. The bulk of the water it moves goes sideways. Now put a persistent clockwise wind over an ocean. Over the Beaufort Sea, there is one, and it has a name. The Beaufort High, a region of high atmospheric pressure that sits over the Canada Basin more often than not, particularly in winter. High pressure in the northern hemisphere means clockwise circulation, so the winds around the Beaufort High run clockwise. Turn each of those wind vectors 90 degrees to the right, and every one of them points inward toward the center. The water converges. It has nowhere to go but down. This is Ekman pumping, and in the Beaufort Gyre it's been measured, both directly and by reconstruction from wind fields. During strong forcing periods, the downward velocity reaches something like 2 to 4 inches a day at the center of the gyre. That is an almost comically slow number. A snail moves faster, but it doesn't stop, and it operates across an area larger than the state of Alaska, and it's been doing it for years on end. 2 inches a day across an area that size adds up to a staggering volume of water pushed downward every year. And this is where the fresh water gets trapped. The convergence doesn't just push water down, it pushes the light surface water down into a column that was previously filled with denser water. The layers get shoved deeper in the middle than they are at the edges. The boundary between the fresh top and the salty bottom, which would otherwise sit at a fairly uniform depth, gets pressed into a bowl shape, shallow at the rim, deep in the middle. Picture the surfaces of constant density inside the ocean as a stack of flexible sheets. At rest, they lie flat. Under the Beaufort High, they get pushed down in the middle, so the whole stack sags into a depression. And the depression is deepest at the center of the gyre. At the middle of the Canada Basin, the surface separating the fresh water from the reference salinity has been pushed down to something like 1,000 or 1,300 feet. At the edges, it's a few hundred. That sagging bowl is the reservoir. Its volume is literally the volume of the depression. Meanwhile, something is happening at the top surface as well, and this one you can see from space. Pile water into the center of a gyre, and the sea surface itself rises there. Not much, a few inches to maybe 2 feet, depending on the year and the strength of the forcing. The Beaufort Gyre has a dome of elevated sea surface at its middle, several hundred miles wide, standing up above the surrounding ocean the way a very shallow watch glass sits above a table. Measuring that dome under a permanent ice cover sounds impossible, and mostly it was, until radar altimeters got good enough to look through the cracks. Satellites like Envisat, and later Cryosat-2 and IceSat-2, fire a pulse downward and time the return. Over open ocean, that's straightforward. Over sea ice, the trick is to identify the leads, the narrow strips of open water that continually crack open between flows, and take the sea surface height from inside those leads. Discard everything that came back off ice, keep the returns from water, and you can build a map of the height of the Arctic sea surface underneath the pack. When Thomas Armitage and colleagues did this systematically for the Arctic, combining Envisat and Cryosat records with satellite gravity data, the Beaufort Dome showed up unmistakably in the maps, and its height tracked the freshwater content measured by the ships beneath it. Two completely independent techniques, one from a research vessel breaking ice in September, and one from a satellite in polar orbit, agreeing on the same signal. That agreement is worth pausing on. It means the height of the sea surface can be used as a proxy for how much fresh water is in the reservoir underneath it, which means the reservoir can be monitored continuously, in winter, everywhere, instead of once a year at a few dozen stations. The empirical conversion factor between the two, worked out by the Woods Hole group, comes to about 33. Roughly speaking, 1 inch of extra sea surface height corresponds to 33 inches of extra fresh water, equivalent in the column beneath it. And the scatter around that relationship contributes only a few percent to the uncertainty in the freshwater estimates. Now the last piece of the machine, and it's the one that turns a pile of water into a current. Water on a rotating planet, if it's piled up somewhere, does not simply slump outward and flatten, it starts to turn. Gravity pulls it down the slope of the pile, the Earth's rotation deflects that motion to the right, And the two forces come into a balance where the water ends up flowing along the slope instead of down it. That's geostrophic flow, and it's the reason weather systems spin instead of just filling in. The dome of sea surface, together with the sagging bowl of density surfaces beneath it, produces a slow clockwise circulation around the Canada Basin. That circulation is the Beaufort Gyre proper. It moves at a few inches per second at the surface. A leaf dropped in it would take years to go around once. Wind pushes water inward. Water piles up. Pile becomes dome. Dome drives current. Current runs clockwise. And the fresh water is inside, going around and around, not going anywhere else. There's the machine, end to end. Which raises the question that took oceanographers about 15 years and a lot of arguing to sort out. Why doesn't it just keep growing forever? Here's the problem in its simplest form. The Beaufort High has been sitting over the Canada Basin, on and off, for as long as anyone has had records. If a persistent clockwise wind pumps fresh water down into a bowl, and the wind never stops, the bowl should get deeper, without limit. Run that calculation naively, and you get a reservoir several times larger than anything ever observed, and a halocline pushed down to depths that don't exist in the real ocean. So something is applying a brake. Two somethings, as it turns out, and the argument over their relative importance ran for the better part of 2 decades. The first candidate came from classical ocean dynamics, and it's called eddy flux. When you tilt density surfaces steeply, you store potential energy in that tilt, and the ocean has a way of releasing it. The tilted flow becomes unstable, curls up, and sheds swirling parcels of water a few miles across that carry the fresh water sideways, out of the bowl and towards the rim. It's the same instability that makes weather fronts in the atmosphere break into cyclones. The steeper you make the slope, the more vigorously the eddies form, and the faster they flatten it back out. That gives you a self-limiting system straight away. Wind steepens the bowl, eddies flatten it, and the gyre settles at whatever depth those two processes balance. For years, that was the standard picture. Then people looked harder at what the ice was doing, and the standard picture turned out to be incomplete in an interesting way. Think about how the wind actually reaches the water in the Arctic. It mostly doesn't. There's a layer of ice in between. The wind pushes on the ice moves, and the ice drags the water underneath it. The stress that spins up the gyre is transmitted through the ice, not applied to the sea surface directly. Now imagine the gyre spinning up. The surface water starts moving clockwise, faster and faster. Meanwhile, the ice above it is being pushed clockwise by the wind at whatever speed the wind can manage. And at some point, the water underneath is moving nearly as fast as the ice above it. When that happens, the drag between them vanishes. There's no relative motion left, so there's no stress. And with no stress, there's no Ekman transport, no convergence, no pumping. The gyre stops spinning up, and nothing had to push back to stop it. The thing that was pushing simply lost its grip. Push it a little further, and the sign flips. If the water gets moving faster than the ice, the water starts dragging the ice instead of the other way round, and the stress reverses, and the Ekman transport goes outward, and the gyre actively spins down. Gianluca Meneghello, John Marshall, and their colleagues at MIT named this the Ice Ocean Governor, and the name is a deliberate reference to a piece of 18th century machinery. James Watt's steam engines had a problem. Take the load off and they'd run away, spinning faster and faster until something broke. The fix was a pair of metal balls on hinged arms, geared to the engine's output shaft. As the engine sped up, the ball swung outward under centrifugal force, and the arms they hung from pulled a linkage that closed the steam valve. Faster engine, less steam, slower engine. It's the first widely used feedback controller in industrial history. It's where the word governor comes from in this sense, and it's the reason a steam engine could be trusted to run a mill unattended. The Arctic has one of these. It's made of ice and water rather than brass, and the feedback runs through drag instead of a valve linkage. But the logic is identical. The faster the gyre turns, the less the wind can drive it. The system regulates itself. What Meneghello and colleagues showed, and what Edward Doddridge and others followed up in more detail, is that this ice-ocean feedback is fast. It acts on a time scale of months, whereas eddies take years to do their work. So on short time scales, the governor is what sets the state of the gyre, and the eddies matter more for the long-term equilibrium. Doddridge laid it out as a three-way balance between wind stress, the ice-ocean governor, and eddy diffusivity, with different terms dominating at different times and in different conditions. Now, here's why that piece of theory suddenly stopped being an academic question. The governor only works if there's ice. Specifically, it works if there's enough ice in a coherent enough pack, moving slowly enough relative to the water, to act as a brake. Take the ice away, and the wind applies its stress directly to the sea surface, and there's nothing to catch up with. The brake is gone. In late summer, when large parts of the Beaufort Sea are now open water, this is no longer a thought experiment. It's the actual condition of the ocean for 2 or 3 months a year. There's a second effect running the same direction. Thick, rigid, well-connected multi-year pack ice transmits stress poorly in some ways and resists deformation strongly. It holds together and moves as a sheet. Thin first-year ice, broken into smaller flows with open water between them, moves more freely and faster, and it responds to wind more readily. Ice drift speeds across the Arctic have increased substantially over the satellite era, and part of that increase is simply that the ice has less internal strength to resist with. Arctic sea ice loss therefore pushes the gyre in two opposite directions at once, and untangling them is difficult. Less ice means the governor weakens, which should let the gyre spin up more. Less ice also means more mobile ice, which changes how efficiently wind stress gets delivered in the first place, and it means more open water, and more open water means more direct wind-driven mixing, and mixing is the enemy of stratification. If you want a clean example of why this subject resists simple statements, that's it. The same physical change, thinner ice, pushes the reservoir in more than one direction at once, and which effect wins depends on the season, the wind pattern, and the state the gyre is already in. What everybody does agree on is the shape of the thing. There is a machine here with a clear architecture, fresh water in from 4 sources, concentrated by a clockwise wind field into a bowl, held there by geostrophic rotation, regulated by a feedback between ice and water, and drained slowly by eddies at the rim. It has an equilibrium. It has a response time. It has, in principle, a maximum size. And between the early 2000s and the mid-2010s, it got much bigger than anyone had previously recorded. How anybody established that deserves working through slowly, because the answer is far from obvious, and it is honestly the most impressive piece of the whole business. Every August, a Canadian Coast Guard icebreaker called the Louis S. St. Laurent leaves port and heads north into the Beaufort Sea. She's a big ship, a heavy icebreaker, and she's been doing this run every summer since 2003. The 2025 season was the 23rd consecutive year. The program is a joint effort between Woods Hole Oceanographic Institution, Fisheries and Oceans Canada, and the United States National Science Foundation, and its job is simple to state and grinding to execute. Go to the same set of positions in the Canada Basin every year, and measure the water column the same way. The core instrument is a rosette. It's a frame, roughly the size of a phone booth, ringed with gray plastic bottles, with a package of sensors bolted into the middle, measuring conductivity, temperature, and depth. The winch pays it out over the side and down through 2.5 miles of water. And on the way back up, The operator fires the bottles at chosen depths, each one snapping shut around a sample of water from a known place in the column. Those samples get analyzed for salinity, for oxygen, for nutrients, for the isotopes that fingerprint where the water came from. A single deep cast takes hours. A survey season involves dozens of them, in ice, in fog, in weather, on a ship that has to break its way to each station. Those casts are the backbone of the whole program. Around them sits everything else. There are moorings on the seafloor, at 3 or 4 fixed sites depending on the year, sitting at depths around 12,000 feet. Each one is an anchor, a long wire, a string of instruments, and a set of glass spheres for flotation, and it stays down there for a full year at a time. Bolted to each is a device called a McLean moored profiler, which is a small robot that crawls up and down the mooring wire on its own schedule, taking a full profile of temperature and salinity every few hours through the depth range that matters. Near the top of each mooring is an upward-looking sonar, pinging the underside of the ice and timing the echo, so that as the pack drifts over the site, the instrument records a continuous transect of ice thickness. On the bottom sits a pressure recorder, measuring the weight of the entire water column above it, which is how you detect changes in sea surface height from below. Once a year, the ship comes back, sends an acoustic signal. The mooring releases its anchor. The floats bring it to the surface, and a year of data comes aboard. Then, a fresh one goes over the side. If the release fails, or the ice moves wrong, or the timing slips, you lose the year. Then there are the ice-tethered profilers, dozens of which have been deployed since the prototype went out. They're cheap by oceanographic standards, they drift with the pack, they profile automatically, and they transmit by satellite, which means they keep reporting through the winter when no ship can reach them. They are the reason the Arctic winter stopped being a data hole. Above all of that, satellites. Radar altimeters reading sea surface height through the leads. Passive microwave sensors mapping ice extent every day since 1979. Laser altimeters and radar altimeters together giving ice thickness. The GRACE gravity missions, which measure changes in the mass of water in a region by detecting the resulting tug on a pair of satellites flying in formation. Put gravity-derived mass change together with altimetry-derived height change, and you can separate the part of a sea level signal caused by adding water from the part caused by making the existing water less dense. And underneath the whole structure, reanalysis, the process of taking every observation of the atmosphere and ocean available and using a physical model to produce a gridded, dynamically consistent estimate of the state of the system through time. Reanalysis is where the wind fields come from that let anyone calculate Ekman pumping for years when nobody was standing there with an anemometer. Taken together, the apparatus comes to this: ships, moorings, robots on wires, robots frozen into ice, satellites in polar orbit, and a great deal of computing. It's worth being clear about what this kind of program buys you and what it costs. It doesn't produce discoveries most years. Most years, it produces another point on a graph. The scientific payoff of the 12th annual survey is invisible at the time and enormous in retrospect, because a single survey tells you what the ocean looks like, and only a long series of identical surveys tells you what it's doing. And that's precisely the kind of program that's hardest to keep funded, because it can never promise a result. There's a real tension in how science gets paid for, and monitoring sits on the wrong side of it. Every few years, somebody has to argue, again, that the 24th year of measurements is worth the ship time. My own view is that the record built in the Canada Basin over the past 2 decades will end up being worth more to future scientists than most of the individual papers written from it, and that the people who kept renewing that argument deserve a share of the credit for everything that follows. Because here's what it gave us. Before 2003, the picture of the Beaufort Gyre came from a scattered, heroic, and deeply uneven set of sources. Soviet drifting stations, the North Pole series, which put teams of researchers onto ice floes and let them drift for months or years while taking hydrographic casts through holes in the ice. American and British submarines running under the pack during the Cold War, collecting ice draft data and occasionally water properties, much of which stayed classified for decades. Aircraft landings on the ice with a winch and a wire, icebreaker cruises when a nation felt like paying for one. Out of all that, oceanographers assembled climatologies, averaged pictures of what the water column typically looked like in a given region during a given era. The 1970s climatology for the Canada Basin, built mostly from Soviet and North American work during that decade, is the baseline against which the modern change gets measured. It's a good baseline, and it is not as good as a modern survey. The station coverage was sparser, the instruments were less precise, and the sampling was concentrated in certain seasons and certain places. When you read that the Beaufort-Gyre's freshwater content has increased by 40% relative to the 1970s, that comparison is doing real work across a genuine gap in data quality, and everyone who publishes it knows it. The strength of the modern claim rests somewhere else, on the internal consistency of the record from 2003 onward, where the same box was surveyed the same way, with the same instruments by the same program for a decade and a half, and the number went up almost every year. So here are the numbers, with the error bars attached, because the error bars are part of the finding. In 2003, the first survey year, the freshwater content of the Beaufort-Gyre box came out at 16,900 cubic kilometers, give or take 1,400. It rose almost every year after that, not monotonically. There was a drop in 2013, a loss of about 1,600 cubic kilometers in a single year, which was itself a significant event and a useful one, because it showed the reservoir could shed water quickly under the right conditions. But the trend across the record was strongly upward. By 2016, the figure had reached 23,200 cubic kilometers, give or take 1,800. The 2019 estimate came in at 23,300, with a much wider uncertainty of about 3,000, reflecting a thinner set of observations that year. Net change across those 16 years, roughly 6,400 cubic kilometers of additional fresh water. Average accumulation rate, 397 cubic kilometers a year, plus or minus 116. Against the 1970s climatology, that's an increase of about 40%. Let me give the gain alone a shape you can stand next to. 6,400 cubic kilometers spread evenly across the lower 48 states would put every square foot of the continental United States under about 2.5 feet of water, and that is only the gain. The full reservoir would put the same territory under something closer to 9.5 feet. Now the caveats, and one of them reshapes the claim. First, the uncertainty on the annual figures is not small. 1,400 cubic kilometers of uncertainty on a 16,900 cubic kilometer estimate is about 8%, and in the sparser years, it's worse. That uncertainty comes from several places: the finite number of stations, the interpolation between them, the vertical resolution of the profiles, the conversion from sea surface height where altimetry is being used, and in the earlier years the patchier coverage of the moorings and profilers. But the year-to-year uncertainties are largely correlated, because the same box gets surveyed the same way each time, which means the trend is far better constrained than any individual year. This is a standard and important point about long records. You can be quite uncertain about the absolute value and still be confident about the change, provided your errors are systematic rather than random. A bathroom scale that reads 3 pounds heavy will still tell you accurately whether you gained weight this month. Second caveat, and this one costs the story something. The Beaufort-Gyre gained fresh water. The Arctic Ocean as a whole gained much less than the Beaufort-Gyre did. Assessments covering the full basin over the 2010s found that the freshening in the gyre was partly compensated by a reduction in freshwater content across the rest of the Arctic Ocean. Water was being concentrated into the western basin as much as it was being added to the Arctic overall. The rivers pour into the Siberian shelves. The wind field determines whether that water crosses the pole with the transpolar drift and heads for the Atlantic exits, or gets pulled around into the Canada basin and pumped down into the bowl. That distinction matters more than it might sound. If the Arctic were simply accumulating fresh water everywhere at a rate of 400 cubic kilometers a year, you'd be looking at a system loading up with new material from rivers and melt. If instead a good share of the gyre's gain is redistribution, existing Arctic fresh water being gathered into one place, instead of released steadily southward, then what changed is not primarily the supply, it's the storage. And a storage change is reversible in a way a supply change is not. Water that was gathered by wind can be scattered by wind. That's the version of this story the evidence actually supports, and it's less like a bathtub filling and more like a snowdrift, which is a temporary arrangement of material that was already there, held in a particular shape by a wind that will not blow forever. Third, the region definition. Everything I've quoted comes from that one box between 70 and 81 north and 130 and 170 west, deeper than 1,000 feet. Move the box and the number moves. Extend the depth of integration and the number moves. Studies that quote around 45,000 cubic kilometers for the Canada basin aren't contradicting the 23,000 figure. They're counting a bigger volume of ocean with a different set of conventions. Anyone comparing two published freshwater numbers without checking the box definitions is going to reach a wrong conclusion, and this happens constantly in second-hand accounts of the subject. With all of that on the table, the finding stands. Something on the order of 6,000 cubic kilometers of extra fresh water accumulated in the western Arctic across the first 2 decades of this century. The accumulation was real. It was measured by multiple independent methods that agree with one another, and it represents the largest such buildup in the observational record. The next question is why, and the answer turns out to have less to do with melting ice than most people assume. If you had to attribute the buildup to a single cause, it would be the wind, and specifically, its refusal to change. Starting around 1997 and continuing, with wobbles, for the better part of 2 decades, the atmospheric circulation over the Canada basin locked into a persistently anticyclonic pattern. The Beaufort High sat where it sits, stronger than average and more consistently than average, and it kept the clockwise wind field over the gyre running year after year, without the extended reversals that the earlier record shows. 2 decades is a long time for an atmospheric pattern to hold. It's long compared with the response time of the gyre, which is where the consequence comes from. If the wind reverses every 4 or 5 years, the reservoir never gets far from equilibrium. It fills a bit, drains a bit, and averages out. Hold the forcing steady for 20 years, and the system has time to run all the way toward the state that forcing implies. Call that the primary term, persistent forcing, integrated over a long time. The second term is more specific and more interesting, and it involves a river changing direction. The Mackenzie River comes out of Canada's Northwest Territories into the southeastern Beaufort Sea, carrying its 300 cubic kilometers a year of fresh water plus a heavy load of sediment. Where that plume goes after it hits salt water gets decided by the wind over the shelf that summer, and the river itself has no say in it. Under one wind pattern, the plume gets pushed east, hugging the coast, moving toward Amundsen Gulf and the Canadian Arctic archipelago. Under another, it gets pushed west and offshore, out over the shelf break and into the deep Canada basin, where the gyre's circulation can capture it. Across the accumulation period, the winds favored the second option. Model work supporting the Woods Hole analysis found a wind-forced redirection of Mackenzie discharge from predominantly eastward flow to predominantly westward flow, with Mackenzie water taking a little over a year to show up in the Gyre region after leaving the river mouth. Think about what that means. The river didn't get bigger. The ocean didn't gain any additional water from Canada. What changed was the destination. Water that used to leave the Arctic reasonably promptly through the Canadian channels was instead diverted into the reservoir and parked there. That single mechanism is a clean illustration of the redistribution point. A change in where existing freshwater goes can look. From inside the box, you happen to be measuring, exactly like a change in how much fresh water exists. The third term is Pacific. The Bering Strait throughflow strengthened through the 2000s, and the freshwater flux through it rose with it, and the analyses of the Gyre's growth pick up an increasing Pacific contribution, particularly from around 2008 onward. More fresh water arriving from the south, entering a basin whose circulation was configured to hold on to it. Fourth, sea ice. Net melt contributed on the order of 500 cubic kilometers to the buildup, roughly 8% of the total. Real, measurable, and considerably smaller than most people expect. I find that 8% figure clarifying because the popular version of this story runs straight from melting ice to freshwater flood to ocean circulation collapse, and the actual accounting doesn't support the first link. The Beaufort Gyre's growth was overwhelmingly a circulation phenomenon. Ice melt was a minor contributor to the volume. Where ice loss does matter enormously is in the machinery rather than the inventory. Thinner ice, more open water, and faster ice drift change how efficiently the wind couples to the ocean, they weaken the governor that regulates the gyre, and they alter how much stirring the surface layer experiences in summer. So the ice decline is deeply involved in this story. Its involvement runs through the dynamics, not through the water balance. Now, what about the Siberian rivers? Over the 2003 to 2018 window, their contribution to the gyre specifically was close to negligible, which surprises people. The Lena and the Yenisei and the Ob are far bigger than the Mackenzie, but their water enters on the Eurasian side, and whether it reaches the Canada Basin depends on the pathway of the transpolar drift, the great current that runs from Siberia across the pole toward the Fram Strait exit. The position of that drift shifts. Under one atmospheric configuration, it carries Siberian river water toward the Atlantic exit and out. Under another, it swings the pathway around toward the Canadian side and delivers it into the Beaufort circulation. During the buildup period, the drift mostly took the first route, and Siberian water largely bypassed the reservoir. You can trace this directly. Siberian river water carries a chemical signature in its dissolved organic material and its oxygen isotopes, and researchers have used those markers to separate the contributions of individual rivers to different parts of the Arctic. It's a beautiful application of chemistry to a physical question. You take a water sample from the middle of the Arctic Ocean, and you can say, with reasonable confidence, that this proportion of the fresh water in it came from the Lena. Assembled, the picture looks like this: wind that wouldn't change, holding the reservoir in a filling configuration for 20 years. A river diverted offshore into the reservoir instead of past it. A strengthening Pacific inflow feeding the system from below and behind. A modest contribution from ice that melted and didn't reform. And a distribution of Siberian water that mostly went the other way. Every one of those terms is a circulation term. Change the circulation, and every one of them changes sign. Which is exactly what people mean when they talk about a release. Nothing bursts. The wind field reorganizes, and everything that flowed in starts flowing the other way. And we know that can happen, because it has been watched. In 1997, Andrei Proshutinsky and Mark Johnson published an analysis of Arctic circulation that reorganized how people thought about the basin. They'd taken decades of sea level pressure data and ocean model runs and looked for structure in the way the Arctic's wind-driven circulation varied. What they found was that it didn't drift randomly. It flipped between two preferred configurations, and it spent multiple years in each one before switching. In the anticyclonic regime, Bobitziu, Espin, the Beaufort High dominates. The winds over the Canada Basin run clockwise, the gyre spins up, and the Arctic accumulates fresh water in its western basin. In the cyclonic regime, low pressure takes over the central Arctic. The winds reverse to counterclockwise. The Ekman transport diverges instead of converging, and the reservoir drains. Fresh water leaves the Beaufort region, spreads across the basin, and heads for the exits. Each regime tended to hold for 5 to 7 years, giving an overall cycle of roughly 10 to 15 years across the 20th century record. That's the framework, and it's worth being careful about its status. It's a well-supported description of a real pattern in the historical data, and it's not a law of nature. The Arctic isn't obliged to keep alternating on schedule. The regimes were identified statistically from a record of finite length, and the physical mechanisms driving the switch are not fully pinned down. What the framework buys you is a strong expectation that the anticyclonic state is temporary, based on the fact that it has always been temporary before. By that framework, the current anticyclonic period is a serious outlier, not because of what it did to the reservoir, though that's remarkable enough, but because of how long it went on. 20 years is roughly 3 times the typical duration. Now, the previous flip is the interesting one because it was partly observed, and it has been reconstructed in detail. Through the 1980s and into the mid-90s, the Arctic ran cyclonic. The Beaufort High weakened, the gyre relaxed, and the fresh water that had accumulated during the preceding decades came out. A team led by Jiaxu Zhang at Los Alamos National Laboratory went after that event with a technique that's essentially chemical dye, done in software. They ran a global ocean and sea ice model and tagged the water in the Beaufort Gyre with passive tracers, particles that get carried along by the flow without affecting it, so that wherever that water went afterward, they could identify it and count it. Then they watched where it went between 1983 and 1995. The answer, and this is the part I'd underline, was that most of it did not leave through the wide Atlantic gateway east of Greenland. It went through the Canadian Arctic archipelago, down through the channels between the islands, into Baffin Bay, out through Davis Strait, and into the Labrador Sea. That routing matters more than almost anything else in this subject, and here's why. Water leaving through the eastern gateway heads south along the Greenland coast in a cold, fast boundary current, and much of it stays in that current for a long time before it mixes anywhere consequential. Water leaving through the Canadian route arrives at the Labrador Sea from the northwest, onto the shelves, into a region where the deep ocean gets ventilated in winter. It gets delivered, in other words, directly to a place where surface salinity has consequences for what the water column does. The magnitude the Los Alamos study found for that historical event, a freshening of about 0.2 parts per thousand on the western Labrador shelves, and about 0.4 in the Labrador Current itself. Those numbers cut both ways, and both edges are worth handling. 0.4 parts per thousand is a real, detectable, oceanographically meaningful salinity change. It's the kind of anomaly that shows up clearly in a hydrographic time series and that physical oceanographers argue about for years. It's also, in absolute terms, small. Labrador sea surface water runs somewhere around 34.5 parts per thousand. A change of 0.4 is close to 1%. Nobody standing on a ship could taste it. It didn't turn the Labrador Sea into a lake. The subject badly needs that calibration. A genuine, full-scale, multi-year release of Beaufort Gyre fresh water, one that actually happened and was actually tracked, produced a salinity anomaly of a few tenths of a part per thousand in the receiving region, which is either reassuring or alarming, depending entirely on how sensitive the receiving system is to a few tenths of a part per thousand. And that question, exactly that question, is where the science stops being settled. Before we get there, though, there's an older event worth walking through because it's the closest thing anyone has to a natural experiment on what a big Arctic freshwater anomaly does to the North Atlantic. It was observed at the time by people who had no idea what they were looking at, and it took 2 decades and a very determined oceanographer to piece it together. In the late 1960s, an unusually large volume of fresh water and sea ice left the Arctic through the gateway between Greenland and Svalbard and started moving south. Nobody flagged it at the time. What people noticed in scattered places over the following years was that the water was getting fresher. Weather ships in the North Atlantic, which took hydrographic casts as a routine part of their station keeping, logged salinity values below anything in their records. Fisheries research vessels found the same. The observations were made by different countries with different instruments for different purposes, and nobody put them together, because there was no reason to think a salinity reading off Labrador in 1972 had anything to do with a salinity reading off Iceland in 1968. It took Robert Dixon and his colleagues at the British Fisheries Laboratory in Lowestoft, working through the 1980s, to assemble the whole thing into a single picture. Their 1988 paper is a classic of the field, and what it described was this: a body of anomalously fresh water had left the Arctic in the mid to late 60s, traveled south along the east coast of Greenland, rounded Cape Farewell at the southern tip, moved up into the Labrador Sea, arrived off the Labrador coast in 1971 through 73, continued around the subpolar gyre past Newfoundland, crossed the Atlantic eastward, passed north of Scotland through the Faroe-Shetland Channel in the mid-70s, and finally returned to the Greenland Sea in 1981 and 82, 14 years. A complete circuit of the North Atlantic subpolar gyre by a single identifiable body of fresh water moving at an average of about 3 centimeters per second, which works out to roughly 2 miles a day. They called it the Great Salinity Anomaly, and in Dixon's own assessment, it ranked among the most persistent and extreme variations in global ocean climate observed anywhere during that century. Now, what did it actually do? The most consequential effect was in the Labrador Sea. Deep convection there, the winter process where surface water cools, gets dense, and sinks to a mile or more, weakened badly, and by most accounts stopped altogether for a few years, around 1968 to 71. The fresh cap sat on top. It was too light to sink no matter how cold the winter got, and the annual renewal of Labrador seawater simply didn't happen. That's a real shutdown of a real deep water formation site caused by a real Arctic freshwater anomaly, documented in the observational record. It's the single strongest piece of evidence anyone has that this chain of causation is physically live. So here's the question that matters. How much water was involved? Estimates of the freshwater excess carried by the Great Salinity Anomaly run in the low thousands of cubic kilometers. The salt deficit measured as it passed Labrador in the early 70s comes to something on the order of 70 billion metric tons, and Dixon's team traced roughly 2/3 of that onward through the Faroe-Shetland Channel and back toward the Arctic. Low thousands of cubic kilometers. The Beaufort Gyre took on 6,400 cubic kilometers between 2003 and 2018, and it currently holds around 23,000. That comparison should make you sit up, and it should also make you cautious, because the two situations differ in ways that matter enormously. The Great Salinity Anomaly delivered its fresh water as a concentrated pulse. It moved as a coherent body. It stayed near the surface. It arrived at the convection sites in a few years, and it arrived in winter conditions. Concentration and timing did as much work as volume. A Beaufort Gyre release, if the historical precedent holds, is a slower and messier thing. The 1983 to 95 event unloaded over roughly a decade, took its water out through the Canadian channels and mixed along the way, spread the same volume over twice the time and across a wider area, and the salinity anomaly it produces at any given place is proportionally weaker, which is why the rate, not the total, is the number that actually governs the outcome, and the rate is the number nobody can currently predict. There's one more thing about the Great Salinity Anomaly that deserves saying clearly, because it gets left out of the dramatic retellings. The Atlantic overturning circulation did not collapse. Europe did not freeze. Sea level along the eastern seaboard did not jump. The Labrador Sea convection site shut down for a few years, then restarted when the anomaly moved on. And by the early 1990s, the Labrador Sea was producing deep water more vigorously than at any point in the instrumental record. The system took a substantial hit at one of its most sensitive points, and it absorbed it, and it recovered. That's not an argument that nothing can go wrong. Two further salinity anomalies were identified in the North Atlantic in the 1980s and 90s, so this is a recurring feature of the system rather than a one-off. And an ocean that has absorbed a shock while carrying its historical amount of heat and fresh water is not necessarily the same ocean that would absorb the same shock after decades of warming and freshening on top. But any account of this subject that leaps from Arctic freshwater to catastrophic collapse has to explain why the closest historical analog produced a regional, temporary, recoverable disruption. If your model of the system can't reproduce what already happened, it has no business forecasting what happens next, all of which leaves the present state of the reservoir as the open item, and a result published in 2023 changed how people talk about it. The buildup stopped. Not reversed, stopped. Somewhere in the middle of the last decade, the reservoir quit growing and settled. Peigan Lin, working with Robert Pickard at Woods Hole and colleagues at University College London and the Japan Agency for Marine Earth Science and Technology, published the analysis in Nature Geoscience in May of 2023. They pulled together the hydrographic record from 2003 to 2019, with satellite-derived sea surface height from 2011 to 2019, and looked at what the gyre had done recently rather than across the whole period. What they found was a state transition. The rate at which the dome of sea surface height had been rising slowed down. The freshwater content plateaued, and the circulation itself shifted, moving southeastward, in response to a change in where the regional wind forcing was strongest. The word they used for the new condition was quasi-stable. The gyre is still holding its enlarged reservoir. It's just stopped adding to it. That's an important observation, and it's ambiguous in an uncomfortable way, which is why the paper landed the way it did. One reading is benign. The gyre hit its ceiling. The ice ocean governor and the eddy fluxes are doing their job. The system found the equilibrium that this wind forcing implies, and it will sit there until the forcing changes. Physics working as advertised. The other reading is that a reservoir that has stopped filling is a reservoir in the state it occupies immediately before it starts emptying. Every previous accumulation phase in the historical record ended, and it ended by reversing. The paper doesn't claim to distinguish between those. It reports a transition and identifies what would matter next. And the thing it identifies is the halocline. Because the second finding in that work is more concerning than the plateau, and it got less attention. The cold halocline layer has thinned significantly. Recall what that layer does. Picture a specific slab of cold, relatively salty water, mostly of Pacific winter origin, sitting between the fresh surface layer and the warm Atlantic water below. That slab is the actual barrier. The fresh surface layer provides the buoyancy, and the cold halocline provides the thermal separation that keeps Atlantic heat away from the ice. Lin and colleagues found it thinning and attributed that to two things: a reduced supply of the cold, Benal's dense Pacific winter water that forms it, and increased entrainment of lighter water from the eastern Beaufort Sea as the circulation shifted. The reservoir sits at capacity, and the partition underneath it is getting thinner. Lynn's own framing was that continued thinning of the cold halocline layer could modulate the present stable state and allow for a freshwater release. That's carefully hedged language, and the hedging is appropriate because the mechanism connecting halocline thinning to release remains a plausible physical pathway awaiting verification, well short of a demonstrated causal chain. Meanwhile, on the other side of the Arctic, a related process has been underway for longer and is better documented. Igor Polyakov and a large international group published work in Science in 2017 showing that in the eastern Eurasian basin, north of Siberia, the halocline had weakened substantially. The Atlantic water layer had shoaled toward the surface, and winter mixing was reaching down into it. Heat from the Atlantic layer was getting up into the surface layer and slowing winter ice formation at a rate the authors found comparable to the direct thermodynamic effect of a warming atmosphere. They called it Atlantification, and it means the eastern Arctic is losing the very stratification that makes it an Arctic Ocean. More recent work has found signs of the same process advancing eastward into the Amerasian side of the basin. Put the two together, and you get the shape of the modern Arctic. On the Eurasian side, the barrier is eroding, and Atlantic heat is coming up. On the American side, a huge reservoir of fresh water sits behind a barrier that's getting thinner, while the wind holds the whole arrangement in place. Neither of those is a prediction of catastrophe. Both of them are observed changes to the structural elements that make the Arctic Ocean work the way it does, measured with instruments over decades by more than one group. And a system whose structural elements are all changing at once is a system where the next transition is harder to forecast, not easier. The honest position sits right there. The gyre has been in an unprecedented configuration for 20 years. It recently changed state in a way nobody predicted in advance, and the physical barriers that govern its behavior are not what they were when the current phase started. So what actually happens if it lets go? That question deserves a careful answer. And careful here means separating three things that get run together constantly: how much water there is, how fast it can leave, and what the receiving ocean does with it. Start with how much water is actually available to move, because the headline figure overstates it badly. The Beaufort Gyre holds around 23,000 cubic kilometers of freshwater equivalent. It also held around 16 or 17,000 in the 1970s, when the Arctic was in what everyone would call a normal state. And it held roughly that much when the survey program started in 2003. That baseline isn't going anywhere. A gyre in equilibrium under a normal wind field still has a bowl of fresh water in it, because the bowl is what a gyre is. Even a full swing into the cyclonic regime doesn't drain the Canada Basin down to Atlantic salinity. It relaxes the dome and lets the excess go. The quantity that could plausibly be released, then, is the anomaly. 6,400 cubic kilometers measured since 2003, or something closer to 8,000, if you take the buildup from the early 1990s, which is the figure that gets quoted in a lot of coverage. 8,000 cubic kilometers is roughly a Lake Michigan and a half. It's a very large amount of water. It's also about a third of the number people usually hear, and that gap matters. Quoting the whole reservoir as releasable turns a plausible scenario into an arithmetic error. Second question, how fast could it come out? Here the baseline is what matters. The Arctic already exports something on the order of 5,000 to 6,000 cubic kilometers of liquid fresh water a year through its two southern gateways every year as a matter of routine. Call it the normal operating condition of the ocean. Now suppose the gyre releases 8,000 cubic kilometers of excess. If it comes out over a decade, det kan sauerwurlwarge kanzax. That's an extra 800 cubic kilometers a year on top of the baseline, an increase of maybe 15% in the freshwater delivery to the northern North Atlantic. If it comes out over 5 years, you're looking at something near 30%. If it somehow came out in a single year, it would be a genuine shock to the system, and no mechanism anybody has proposed can do that. The physical constraints on the rate are real. The water has to get out of the Canada Basin, which means crossing the gyre's rim, which is done by eddies and by the relaxation of the geostrophic circulation, and those processes have characteristic speeds. Then it has to transit the Canadian Arctic archipelago, a set of channels with sills and tidal mixing and constrictions, or run the long way around through the Atlantic Gateway. Then it has to make its way down to the convection regions. The historical precedent unloaded over about 12 years. The models that have looked at this find similar timescales. Nobody serious is describing a sudden event. Third, and this one gets misunderstood constantly, what would a release physically do to anything at the surface? Nothing. Nothing at all, in the sense the word flood normally implies. This water is already in the ocean. Moving it from the Canada Basin to the Labrador Sea changes global sea level by exactly 0, because no water is being added to the ocean and none is being taken away. Nothing gets inundated. No coastline sees a wave. If you were standing on the shore of Newfoundland at the height of the event, you would see the same ocean you always see. The effect is entirely a matter of density in the upper few hundred feet of water, and it's a small one in absolute terms, a few tenths of a part per thousand as the historical case showed. What that small change does, and this is the whole reason anybody cares, is alter the buoyancy of the surface layer in the one place on Earth where surface buoyancy controls the vertical circulation of half an ocean. There's a fourth question underneath all of it, and it's the one with the least satisfying answer. Where would the water go? The 1980s event went through the Canadian channels, into Baffin Bay, into the Labrador Sea. But the routing depends on the wind field during the release, on the state of the archipelago's through flow, and on where in the gyre the water is when the reservoir relaxes. The Woods Hole Group's own summary of their 16-year analysis put it plainly. It remains an open question when and how the fresh water is released from the Beaufort Gyre region, and what pathways it subsequently follows. That's the state of knowledge, stated by the people with the best data on the planet about it. Open question. When, how, and where? Modeling work published in 2024 looked at exactly this, running wind perturbation experiments to see what triggers release and where the water ends up. The finding was that a cyclonic wind anomaly associated with a weakened Beaufort high does trigger release, and that both the export and the subsequent renewal of the gyre's water depend on where the wind anomaly sits and how long it lasts. Different perturbations in the same model produce meaningfully different outcomes. An honest summary of the release side of this subject reads roughly like this. There is an excess of something like 6,000 to 8,000 cubic kilometers of fresh water in the Western Arctic, measured with good instruments and reasonable error bars. The mechanism that would let it go is understood in outline and has operated before within the instrumental record. The timescale of a release is probably in the range of a decade based on one historical case and a set of model experiments. The routing is uncertain, the trigger is uncertain, and the timing is completely unknown, all of which keeps the story inside the Arctic. The moment that water crosses into the Atlantic, the science stops being a matter of measurement and becomes a matter of argument. The Atlantic does something the Pacific does not do, and it's the reason Northern Europe is habitable. Warm surface water moves north up the western side of the Atlantic and then across it, carrying heat out of the tropics. Somewhere in the far north it gives that heat up to the atmosphere, becomes cold and dense, sinks to 2 miles or more, and then flows back south along the bottom, all the way to the Southern Ocean. Water comes north on top, goes south underneath, and the difference between them is a net transfer of heat from the equator toward the pole. Oceanographers call the whole arrangement the Atlantic Meridional Overturning Circulation. In practice, everyone says AMOC. The number attached to it is about 17 Sverdrups, which is 17 million cubic meters of water per second, moving north across the latitude of Florida and the Canary Islands. That's on the order of 100 times the combined flow of every river on Earth. The heat it carries, at that latitude, is about 1.2 petawatts. A petawatt is a quadrillion watts. Ben Mote at the United Kingdom's National Oceanography Center, one of the people who runs the array that measures it, describes the figure as equivalent to about 1 million power stations. That heat doesn't stay in the water. It gets released into the atmosphere over the North Atlantic and gets carried east by the prevailing westerlies. And it's a substantial part of why Britain and Norway have the climate they have, instead of the climate their latitude would otherwise suggest. London sits further north than Calgary. Oslo sits further north than Anchorage. Neither of them behaves like it. Worth being precise about one thing, since it's a common muddle. The Gulf Stream itself is mostly wind-driven. It would keep flowing even if the overturning stopped, because it's an inevitable consequence of the wind field over a rotating ocean basin with a western boundary. What the overturning adds is the northward extension of that warmth into the subpolar and Nordic regions, and the sinking limb that pulls more warm water north to replace what went down. So a weakened AMOC doesn't stop the Gulf Stream. It changes how much of the Gulf Stream's heat gets delivered to high latitudes and how much of the return flow happens at depth. Now, why does salt matter? Because sinking requires density. And density in cold water is almost entirely a matter of salt. Here's the sequence at the northern end. Warm, salty water arrives from the south. It's salty because it spent time in the subtropical Atlantic, where evaporation exceeds rainfall and the ocean concentrates its salt. It's warm. So despite the salt, it's still buoyant. Then it moves north and gives up heat to a cold atmosphere. Cooling makes it denser. And because it was already salty, cooling is enough to push it past the density of the water underneath, and it sinks. Take away the salt, and that last step fails. Water can be cooled to the freezing point and still be too fresh to sink through the layer beneath it, in which case it just sits on top and eventually freezes. That's the Arctic condition, and it's what fresh water does to a convecting basin. It turns it into a stratified one. The whole hypothesis fits in a single paragraph. Arctic freshwater reaches the North Atlantic convection sites, caps them, deep water formation weakens, and the overturning slows. It isn't a fringe idea. Henry Stommel worked out in 1961 that a circulation driven by competing temperature and salinity gradients can have more than one stable state and can flip between them. And that finding has been the theoretical backbone of the field ever since. Paleoclimate records from Greenland ice cores show one abrupt northern hemisphere temperature swings during and after the last glaciation, and the leading explanation for several of them involves large freshwater discharges from melting ice sheets disrupting the North Atlantic circulation. Model experiments where researchers artificially dump fresh water into the subpolar Atlantic, which the field cheerfully calls hosing, reliably weaken the overturning. And there's the Great Salinity Anomaly, which did exactly this at regional scale within living memory. The physical chain, then, is sound in principle, supported by theory, present in the paleoclimate record, and equipped with an observed modern analog. Now the trouble. There are 3 separate places where that chain, applied to the Beaufort Gyre in the 2020s, runs into evidence that doesn't cooperate. The first is about where the overturning actually happens. The second is about whether the observations show the trend the models predict. The third is about how much of the whole picture rests on models whose Arctic behavior we can independently check, and how well they do when we check it. None of these say the concern is misplaced. All 3 change what an honest forecast is allowed to claim. For most of the second half of the 20th century, if you asked an oceanographer where the Atlantic's deep water gets made, the Labrador Sea would have come up first. It's the obvious candidate. A deep basin, surrounded by cold land, taking brutal winter winds straight off Canada, and observed to convect down to 1.5 miles in hard winters. It shows up as the dominant sinking region in a great many climate models. and it sits exactly where Arctic fresh water arrives. That last point is what makes the Beaufort-Geier story so compelling. Fresh water leaves the Arctic through the Canadian channels, arrives in the Labrador Sea, caps the convection, weakens the overturning. Every link lands on a target. In 2014, an international consortium put a line of moorings and gliders all the way across the subpolar North Atlantic, from Labrador to Greenland to Scotland, to measure the overturning directly where it was supposed to be happening. The program is called OSNAP, for Overturning in the Subpolar North Atlantic Program, and it was led by Susan Lazier. In 2019, they published the first 21 months of results in Science, and the paper's title told you what they thought of them: a sea change in our view of overturning in the subpolar North Atlantic. The overturning was happening in the eastern part of the array. The Erminger Sea between Greenland and Iceland the Iceland Basin east of that were where the warm, salty Atlantic water was being converted into cold, dense, southward flowing water. The Labrador Sea contribution to the total, and to its variability, was much smaller than anyone had expected. That result caused a serious rethink. It didn't eliminate the Labrador Sea from the picture. What it did was undercut the specific pathway from Arctic fresh water to overturning that so many people had been reasoning from. If the Labrador Sea isn't the main engine, then capping the Labrador Sea doesn't stop the engine. It also raised an awkward question about the models. If climate models put the bulk of subpolar overturning in the Labrador Sea, and the observations put it in the Erminger and Iceland basins, then the models are getting the geography of the process wrong, and their sensitivity to a freshwater anomaly delivered to the Labrador Sea might be wrong along with it. Matthew Maneri and colleagues took that question on directly in 2020, comparing the OSNAP observations against a large set of climate models, and found the picture more reconcilable than the headline suggested. The models weren't as wrong as the sharpest reading implied. And the relationship between Labrador Sea processes and the wider overturning is more indirect than a simple engine metaphor allows. Then, a 2021 paper in Science Advances argued for what its authors called an outsized role for the Labrador Sea in the multi-decadal variability of the overturning, on the grounds that a 21-month record captures short-term variability, while the Labrador Sea's influence works over decades. And more recent work has reported Labrador Sea overturning strengthening over recent decades in association with freshening below the surface, which is not the direction the simple hypothesis would predict at all. I've laid that sequence out at length because the sequence is the point. This is a live scientific argument, conducted in the literature, between good groups with good data, and it is not resolved. What OSNAP established beyond dispute is that the subpolar North Atlantic does not work the way the textbook diagram said it did. What it has not established is exactly how it does work, or how sensitive the real system is to fresh water arriving from the northwest. Which means the last link in the Beaufort-Geier chain, the one that connects Arctic fresh water to global ocean circulation, is currently the weakest link in it. The physics remains entirely plausible. The specific geography of the process turned out to be different from what the reasoning had assumed, and the field is still working out what that implies. Now the second problem, and it's the one I think most people would find hardest to believe. Since 2004, there has been a line of moored instruments stretched across the Atlantic at 26.5 degrees north, from the Bahamas to the Canary Islands. It's called the Rapid Array, and it does something that had never been done before. It measures the entire overturning circulation continuously at one latitude. The way it works is elegant. You don't need to measure the velocity of every cubic meter of water crossing the line. You need the density profile at each end of the basin, plus the flow through the Florida Straits, which is measured by a submarine telephone cable, plus the wind-driven surface transport, which you get from satellites. Combine them, and geostrophy gives you the rest. The array has been running for over 20 years now. It is the single most important instrumental record in this entire subject. And what it shows is complicated enough that it has caused the Intergovernmental Panel on Climate Change to soften its language. The first few years of rapid data produced a shock, and it had nothing to do with trends. The overturning turned out to be enormously variable on short timescales. The steady conveyor belt of the textbook diagrams turned out to be a flow that could swing by 10 sphere-drups within a single year, and by several sphere-drups between 1 month and the next. The mean across the record from 2004 to 2020 came out around 16.9 sphere-drups, and individual monthly values ranged across a band wide enough that the average tells you very little about any particular month. In the winter of 2009 into 2010, there was a downturn of about 30% that lasted a year. At the time, it caused genuine alarm. Then, it recovered. That variability is the central practical problem in this whole field, and it has an unglamorous name: signal to noise. If a system naturally swings by 10 sphere-drups a year, and you're looking for a forced trend of maybe 1 sphere-drup per decade, you need a very long record before you can distinguish one from the other. 20 years might not be enough. Analyses of exactly this question, using the rapid record alongside model estimates of natural variability, have argued that detecting an anthropogenic trend at that latitude with confidence requires several decades of continuous observation. So what does the record say? Taken from 2004 through 2023, it shows a weakening of about 1 sphere-drup per decade, and that trend is statistically significant at the 95% level. Different treatments give values ranging from around 0.4 to 1.6 sphere-drups per decade, and the path it took to get there is not a straight line. The first 8 years or so showed strong weakening. Then from roughly 2010 through 2018, the circulation strengthened again. Then it resumed weakening. Anyone who had drawn a trend line in 2012 would have made a confident prediction that the following 6 years falsified. That zigzag is precisely why the Intergovernmental Panel on Climate Change wound back its confident statements about observed decline. Its position now is that it has low confidence in a weakening of the overturning during the 20th century, which is a striking thing for a body assessing a phenomenon this consequential to have to say. Meanwhile, the indirect evidence points harder. Because direct measurements only go back to 2004, researchers have built proxies to reach further into the past. The most discussed is a fingerprint method. A weakened overturning should leave a distinctive spatial pattern of sea surface temperature in the North Atlantic, specifically a cool patch south of Greenland, where less warm water is arriving, while nearly everywhere else warms. That cool patch really is there in the sea surface temperature record, and it's been there for decades. And it's one of the very few regions of the global ocean that has not warmed. Reconstructions built on that fingerprint, associated with Lev Caesar and Stefan Rahmstorf among others, suggest a substantial weakening across the 20th century. Other reconstructions, built on different assumptions, disagree flatly. A 30-year reconstruction published in 2021, using boundary density anomalies to extend the estimate back to 1981, found no overall decline across the record, with the weakest period being the observed downturn between 2008 and 2012. Its authors argued that capturing changes in the deep part of the circulation is essential for detecting a real trend, and that methods focused on a single layer can mislead. Two careful groups, two defensible methods, opposite answers about the 20th century. And then there are the collapse projections, which are their own category of argument. A 2023 analysis using statistical early warning signals in the sea surface temperature fingerprint put a collapse somewhere in a window running from the 2030s to the 22nd century, with a central estimate uncomfortably soon. It attracted immediate and substantial criticism about whether the statistical method is valid for this kind of system and whether the underlying data can support it. A 2025 paper using a different approach found a shutdown before 2100 unlikely. Work published in Environmental Research Letters has pointed out that if you run the models past 2100 instead of stopping there, a shutdown eventually occurs in a large majority of high-emission scenarios, which suggests the question may be less about whether and more about when. The official assessment sits in the middle of all that. The overturning is very likely to decline over the 21st century under every emission scenario, which the panel holds with high confidence as a qualitative statement. Whether that decline involves an abrupt collapse before 2100 is held only at medium confidence, and the quantitative projections of how much it declines are held at low confidence. Read that carefully, and you get an unusual epistemic situation. The direction is well supported. The magnitude is poorly constrained. The possibility of an abrupt transition can't be excluded and can't be demonstrated, which brings the third problem into focus, and it's the one that ties back to everything else in this story. All of the projections come from models. The models have to represent the Arctic Ocean, its stratification, its ice, its freshwater budget, and its export to the Atlantic, in order to represent the freshwater forcing that any of this depends on. How well do they do that? Assessments comparing the current generation of climate models against the observed Arctic freshwater record find substantial spread. Models disagree with each other about the size of the Arctic's freshwater store, about how it's distributed, about the strength and behavior of the Beaufort Gyre, and about the magnitude of the export through the gateways. Work examining the Beaufort Gyre specifically across the model ensemble finds a wide range of present-day states and an even wider range of future ones. That spread is an honest reflection of how hard the problem is, rather than a failure of the field. You're asking a global model with a grid spacing of tens of miles to correctly reproduce a wind-driven reservoir whose behavior depends on eddies a few miles across, sea ice mechanics, a narrow, shallow strait, a maze of Canadian channels, and a river plume that turns left or right depending on the summer. But it does mean something specific about the confidence anyone should attach to a forecast. The chain runs, Arctic wind pattern, to gyre release, to export route, to North Atlantic surface salinity, to convection, to overturning strength, to climate. There's real uncertainty at every link, and the uncertainties multiply rather than cancel. So let me set out the ledger, because the value of this subject lies in keeping the columns separate. Measured with instruments, repeatedly, by more than one method, the Beaufort Gyre holds roughly 23,000 cubic kilometers of freshwater equivalent, with an uncertainty of a couple of thousand. It gained about 6,400 of those between 2003 and 2018. The rate of gain averaged just under 400 cubic kilometers a year. The dome of sea surface height above it rose, and then plateaued. The cold halocline layer beneath it has thinned. The Bering Strait throughflow has strengthened. Arctic River discharge has increased. Sea ice extent, thickness, and age have all declined sharply. The overturning circulation at 26.5 degrees north has been directly measured since 2004 and shows a weakening of roughly 1 sverdrup per decade across that record, with large swings on top of it. Overturning in the subpolar North Atlantic is concentrated in the eastern basins, rather than the Labrador Sea, at least over the period observed so far. All of that is observation. You can argue about error bars. You can't argue about whether it happened. Reconstructed from observations, plus a physical framework, with more room for disagreement, the wind-driven mechanism of the accumulation, the regime alternation between anticyclonic and cyclonic states, the routing of the 1980s release through the Canadian channels, the salinity anomalies that release produced in the Labrador Sea, the freshwater contributions attributed to the Mackenzie, to Pacific inflow, and to ice melt. The behavior of the overturning before 2004, modeled, with the uncertainty that implies what triggers the next release, when it happens, how fast the water leaves, which route it takes, how much of it reaches a convection site rather than being mixed away on the journey, how the subpolar North Atlantic responds, what the overturning does in consequence, and what the climate does after that. The gap between column 1 and column 3 is where nearly all the drama in the public version of this story lives, and I don't think that's dishonest so much as a natural consequence of what makes a good headline. A reservoir the size of the Great Lakes held back by wind is an arresting image, and it happens to be accurate. The trouble starts when the certainty of column 1 gets silently transferred to the claims in column 3. What would change the picture? Several things, and they're all being watched. The first is the Beaufort High itself. If sea level pressure over the Canada Basin drops into a sustained cyclonic pattern, the reservoir starts unloading, and that would be visible in atmospheric data within a season. The plateau identified in 2023 means the system is already sitting at the top of its curve, and the wind is the switch. The second is the sea surface height record from satellite altimetry, which gives an almost continuous readout of the reservoir's volume. A sustained drop in the height of the dome is a direct measurement of release, available in near real time, without waiting for a ship. The third is the salinity of the Canadian Arctic archipelago outflow and of Davis Strait, where the moorings sit. Consider that the tap. If a release is coming out that way, the mooring records will show it before anything shows up in the Labrador Sea. The fourth is the OSNAP and rapid arrays, which will keep extending their records, and every additional year improves the ratio between signal and noise. Both of them face the same chronic funding vulnerability as the Arctic surveys, and both of them become more valuable with every year they run. There's an obvious observation to make about all of that. Everything in the list is a monitoring program. Not one of the open questions in this subject is going to be settled by a clever new theory or a bigger computer. They get settled by instruments left in the water for a long time, serviced by people on ships in bad weather, and by whoever keeps writing the funding proposals. I'd go further. The single most useful thing anyone has done for this question in the past 25 years was to decide, in 2002, that somebody should go back to the same spots in the Canada Basin every summer and measure the same things. Everything we now know about the accumulation exists because of that decision. If it hadn't been made, the reservoir would have grown by a Lake Michigan and a half, and nobody would have had a number for it, which raises a question worth carrying around. What else is doing something significant right now that nobody has thought to start measuring? There's a stretch of ocean south of Greenland and east of Newfoundland that has, over the past century, refused to warm. Almost the entire surface of the world ocean has gained heat. That patch has not. On a global map of temperature trends, where nearly everything is shaded in reds and oranges, there's a blue smudge sitting in the subpolar North Atlantic, and it's been there long enough and consistently enough that it has acquired a nickname among climate scientists. They call it the warming hole, or the cold blob. Nobody disputes that it's there. What it means is contested, and the fingerprint reconstructions I mentioned earlier rest on the claim that it's the surface expression of a weakening, overturning circulation delivering less warm water north. Alternative explanations exist, involving aerosols and local heat exchange and ocean heat uptake, but it's the closest thing this subject has to a visible symptom, and it sits directly downstream of everything we've been talking about. Now, what does the overturning circulation actually do for the people living around it? The European part of the answer is the famous one, and it's often overstated. A weakened overturning would cool northwestern Europe relative to where it would otherwise be, in the sense of taking the edge off warming rather than plunging Britain into a new ice age. The disaster movie version, where the Atlantic stops and northern Europe freezes over in a week, has no relationship to anything in the scientific literature. The American part of the answer is less famous and considerably more concrete. When the Gulf Stream flows strongly along the eastern seaboard, the rotation of the Earth holds the sea surface higher on its offshore side than on its inshore side. It's the same geostrophic balance that holds up the Beaufort Dome, working sideways. A fast current on a rotating planet maintains a tilt across itself. That tilt means sea level along the coast, between Cape Hatteras and Nova Scotia, is being held down, slightly, by the strength of the current offshore. Weaken the current, and the tilt relaxes, and the water comes back toward the coast. So a slowdown in the overturning circulation raises sea level along the northeastern United States, over and above whatever global sea level is doing. Researchers including Tal Ezer and Asbury Salinger identified an accelerated sea level rise hotspot along that stretch of coast north of Cape Hatteras and connected it to changes in the Gulf Stream system. And there's an event that made the mechanism uncomfortably concrete. During 2009 and 2010, tide gauges along the coast north of New York City recorded a rise of roughly 4 inches in a single 2-year period, an anomaly described in the subsequent analysis as unprecedented in the tide gauge record. That was the same interval in which the Rapid Array recorded its 30% downturn. A team led by Paul Goddard published the connection in Nature Communications in 2015. 4 inches sounds trivial until you consider what it does to a storm surge in a place like Norfolk, or Charleston, or the back bays of New Jersey. Coastal flooding thresholds aren't crossed by average sea level. They're crossed by average sea level plus tide plus surge, and 4 inches of extra baseline turns a certain number of near misses into floods. That event was temporary. The circulation recovered, and the sea level anomaly relaxed. But it demonstrated in the real world on real tide gauges that a change in the Atlantic overturning circulation shows up on the American coastline within months, in inches, measurably. That's the link most Americans have to this, and it arrives as something very ordinary. A number on a tide gauge in Sandy Hook, read off by an instrument that costs less than a used car. There are others. The subpolar North Atlantic supports some of the largest commercial fisheries in the world, and its productivity depends on the mixing that brings nutrients from depth to the sunlit surface. Convection is part of that mixing. Suppress it, and the ecosystem changes, and cod, capelin, and the fisheries built on them respond to changes in the physical ocean on timescales of years. The North Atlantic is also one of the ocean's most efficient regions for absorbing carbon dioxide from the atmosphere, precisely because it takes surface water and pumps it into the deep ocean where the carbon it carries is out of circulation for centuries. A slower overturning is a slower carbon sink, which feeds back into the atmospheric side of the problem. None of those consequences requires a collapse. They all scale with how much the circulation weakens, and the weakening is the part the assessments consider very likely, which is, I think, the useful reframing of this whole subject. The question that gets asked is whether the Atlantic circulation will collapse, and the answer to that is unknown and probably unknowable at present. The question that matters more is how much it weakens, how fast, and what fresh water from the Arctic contributes to that. Those questions have partial answers now, and they'll have better answers in a decade. And the difference between a 10% weakening and a 30% weakening is measured in coastlines and fisheries and carbon. Follow a single parcel of water through this, and you get a sense of the timescales involved. Say it falls as snow on the Mackenzie's catchment in northern Alberta in October. It sits through the winter. In May or June, it comes down the river in the breakup, brown with silt, and pushes out into the Beaufort Sea. That summer, the wind is out of the wrong quarter, and the plume goes west instead of east, offshore, over the shelf break. 14 months later, it's in the gyre, turning slowly clockwise under the pack ice, somewhere in the upper few hundred feet of the Canada Basin. And there it stays. A decade of slow circles, a few inches per second, in the dark for most of the year, pushed a little deeper every winter by a wind field it will never be aware of. Then the pressure pattern over the Canada Basin shifts, and the dome relaxes, and the parcel drifts east and finds its way into one of the channels between the Canadian islands. 2 or 3 years threading through that maze, mixing with everything else in there, out into Baffin Bay, south through Davis Strait, into the Labrador Sea, sometime in the 2040s, having left the Rocky Mountain foothills before some of the people reading this were born. And in the Labrador Sea, in some February, it participates for the first time in something that reaches beyond the Arctic. It sits at the surface in a winter storm, a little fresher than the water around it, resisting by that fraction the cooling that would otherwise send it downward. Multiply that resistance by a few thousand cubic kilometers, and you have changed by some small amount how much water sinks in the North Atlantic that winter. That's what the fresh water in the Beaufort Gyre actually is when you follow it far enough. It's a delay in the sinking of the North Atlantic, a small adjustment to the ocean's willingness to turn over, made in a place nobody lives, during a month nobody visits. And the North Atlantic's willingness to turn over is one of the small number of physical facts that set the terms of life in the Northern Hemisphere. How much heat reaches Europe, how high the water stands against a bulkhead in New Jersey during a nor'easter, how much carbon the ocean takes out of the air each winter and puts somewhere it can't warm anything for 400 years, where the cod are. Almost none of us will ever see the Canada Basin. There's no reason to go. It's ice for most of the year and gray water for the rest of it. And there's nothing there but instruments and the occasional icebreaker and a great deal of extremely cold, extremely quiet ocean. But every one of us lives downstream of what it does with its fresh water. The Atlantic is the system that connects a wind pattern over the Canadian Arctic to the temperature of a January afternoon in Dublin and the height of the tide at Battery Park. It's the longest lever on the planet with a human being standing at the other end of it. And the fulcrum is a bowl of meltwater and river water and Pacific water held up by air pressure over an ocean almost nobody has ever looked at. The honest ending here refuses both the countdown and the reassurance. What's true is this: a very large quantity of fresh water, precisely measured, sits in a configuration that the historical record says is temporary, connected to a circulation whose sensitivity to it remains one of the open questions in physical oceanography. We'll know more in 10 years, because there are instruments in the water right now that will still be reporting then. I'd rather leave you with that than with a date. If you've got a view on any of this, I want to hear it, and I'd particularly like to hear one thing. Throughout this, the answers we have came from somebody deciding, decades ago, to go back to the same place and measure the same thing over and over, long before anyone knew it would matter. So here's the question I'd put to you. What's something in your own field, or your own town, or your own life that nobody is keeping a record of, and that you suspect somebody will badly wish had been recorded 30 years from now? Put it in the comments. That particular question tends to pull better answers out of people than anything I could come up with on my own, and I go through them. And if the Arctic is the kind of place you want more of, the like button is how you say so, and subscribing means the next one finds you instead of the other way around. There's a great deal more ocean where this came from.